Alright, so it's been a while since I made a video, and just want to give an update. I've been trying a bunch of stuff to try to, simplify the design, and, when we talked last time, I was trying to use this U-Blocks part, which has a PPS, which you can set to different frequencies, and I found that it can be, 1 megahertz or 2 megahertz, and it gives you an output that this is it right here, jitter free. So what I have is I have the U-Blocks, and it's set to be giving me a 2 megahertz locked signal coming out. So this should be traceable to the GPS that's on the satellite. I had wanted to, as we talked about before, use the 1 megahertz, put it through old school PLL, multiply it up by 10 to get my 10 megahertz to drive the reference. And when I did that, it turns out that this 10 megahertz, it was 10 megahertz, but it looked like complete junk. And there's lots of, R's, resistors, capacitors you have to add to the PLL to make it work. And, I have a very, very narrow capture range. And so what wound up happening was, it would try to adjust its 10 megahertz, plus and minus, 10 kilohertz. And so it was very, very susceptible to noise, and it showed up as jitter. I didn't bother making a video about it, so I just kind of ditched that approach and went with a more integrated solutions. So there's this ICS part. They've since been bought by Renesas. And basically this is a clock multiplier where you have here a clock in. All the magic happens inside this chip. There's no external parts. And you set what the multiplication factor is with some bits. And so on this part, you can do, 2, 3, 4, 5, 6, and 8x, and then, 5 and a third and 3 and a third. So there is no 10x, which I need, but there is a nice 5x. And so I've programmed the U-Blocks chip to give 2 megahertz. That's the 2 megahertz. And so I should be able to look at the output of the chip and have a nice 10 megahertz, which is what I have here. And so this is 10 megahertz. So it's 1, 2, 3, 4, 5 edges here, or peaks here for every one there. So this is 10 megahertz like you would expect. And this is the part right here, and you can set what the multiplication factor is with these bits. And so that's 6x. I'm not sure what that is. That's 4x. And immediately you see a problem that there is jitter in there. And so what it's probably doing is it's probably speeding up this clock and then dividing it down. And that's why you get this jumping back and forth over here. And of course it's beating and making noise. That's why the signal looks chunky. But, all I want is my 5x. And when I get that, the edges look kind of clean. You can kind of see some jitter right here, which, again, if you feed this into the Silicon Labs part, that's probably going to attenuate that jitter. And of course, the signals look chunky because of my bad probing discipline. But ignore that for the moment. So this is kind of encouraging. This doesn't require, my complicated system over here. It's boom, there it is. I got my 10 megahertz with just this circuitry. So I'm feeling, kind of like, I don't know, kind of bad, because this is a lot of work, and this sort of does it for you automatically. This guy takes care of disciplining the 2 megahertz coming out. That multiplies it up. I got some jitter. It's going to be attenuated by that. Okay. So the real test is to compare it to an actual stable clock, because I don't know what the inherent jitter of the signal coming out is. I've never compared it to a stable reference to see what the jitter actually is. So let's do that. So what I'm going to do is I'm going to look at the output of my 10 megahertz crystal, which is currently it's plus 40, so it slips a clock at least every 45 seconds. So I can look at the output of my oscillator, which is here, and I know that this is stable because it's a crystal. It doesn't have a high amount of jitter. I forgot what the spec is, but it's very, very low jitter. However, if I look at the signal coming out of, and it's kind of hard to see the way the display is, but what you see is a huge amount of jitter, cycle to cycle, and that this guy, I know it has low jitter, and this jitter is actually occurring on that output clock. It's not occurring on my clock because my clock is stable, and I've looked at it relative to a the store-bought GPS reference, so I know that this doesn't have any jitter because it matches what's coming out of that other device, and this actually does have jitter, which is kind of disappointing. And it's kind of hard to see the jitter because of that edge. So if I look at the reference, this is a 2 megahertz reference, you can see the jitter right here. So it has 10 nanoseconds of jitter on the 2 megahertz coming out, and since this is, and it's hard to see, but here's where the edges lie, and you can see that they're walking that way, and I'm running slow. So that makes sense because these edges are coming, they're 1 clock short, well, every 30 seconds at least, so that these are actually stretched out, and these edges come earlier. That's why they're walking that way, and that whatever count I get here tells you how often this series of edges slips past one of these edges. So the circuit seems to be working, like the theory says. This is walking that way because it's running slow, but it has a huge amount of jitter. So that's unacceptable. Again, probably in the real world, it doesn't matter because this part will attenuate a lot of that jitter out because it's just looking for what the base frequency is underneath all that. But it kind of makes me want to say, you know what, this guy, even without a GPS reference, this guy is very, very stable. It's very, very close to 10 megahertz. It's plus and minus, a fraction of a ppm. This guy doesn't give you an accurate reference without a GPS, and it has all this jitter, and it might be attenuated there, but I'm trying to be the most perfect clock source imaginable. So actually, it is not very satisfying to use this, and that means I'm going to continue to use my method with all of its complexities. I still need to work on the software for the tuning and so forth, but it kind of validates my approach. And yes, this is a quick and dirty way to do it. It would probably be good enough for most applications, but my goal here is actually design something and do a lot of hard work unnecessarily, I guess. And so I'm going to continue with this. And so I'm actually kind of happy that I tried this at least. The PLL was a complete disaster. This new part, it's certainly better, and this is way simpler. I mean, basically, I need this, that, maybe that inverter, and that signal, or that chip, and I have my complete system, which is what's more or less in that, small box. However, I like this because it's mine, and I have my display, I can tune it, and I can just sort of practice engineering by working on this actual design and working on the software to do the auto tuning. So that's where things stand. The next step is to get rid of all this stuff and to get going again on this. The next step is to work on the circuit with the op amp, so that what comes out of the DAC, I make it, a 5-to-1 ratio, so I can tune even finer. I mean, right now I'm at 90 counts, so maybe if I slow it down one more, the granularity here affects my ultimate precision, and so by doing this, by doing the op amp trick, I'll get better ultimate granularity on my tuning. So that's where things stand. I'm glad I'm back into working on my electronics, and I'll have a new video at some point with updates. Oh, actually, while I'm here, I can really make the clock be bad, and so now you can see it. Since I'm going fast, my edges are always occurring earlier, so I see it's walking there. So that's how I know that the GPS is working, and this amount of jitter, 15 nanoseconds. That's kind of actually that 15 nanosecond number comes up a lot. So that's sort of interesting, but good experiment. Onward to the product like I intended. All right. So maybe a video in a week or so when I get the DAC stuff working. All right.